Okay, we continue. Uh, we have done this comparison of this Grace Hopper Grace Blackwell super chip and the MI250X GPU and the MI300A APU. So we continue to continue our discussion. Besides the all these technical evolutions we have discussed about this MI300 APU, there is another feature of this MI300 APU we need to discuss. I mean, Nvidia has used the word super chip to describe their Grace Hopper and Grace Blackwell chips. So we cannot use super chip anymore. But actually, if you look at MI300A, it's another super chip. I mean, the logical design, the high-level logical design is new. It has quite some new technical evolutions. Sometimes we can claim that are technical revolutions. And we didn't discuss the packaging of this MI300 APU. Is a kind of very complex packaging of the CPUs and the GPUs and the HBM memory onto a SIM chip. But anyway, there is some potential we need to discuss, which comes with this specific MI300 APU. If we look at this MI300 APU, we know we have 6 XCDs, let's say 6 GPUs integrated onto the same SIM chip as the CPU. We have 3 CCDs. We have 3 CCDs. There's 3 CPUs. That means 3 CPUs. And we have 6 XCDs. That means 6 GPUs. Okay. All these are chiplets, and all these chiplets are integrated onto the SIM chip, and with a very complex packaging. This the MI300A. But there is something very interesting coming with this kind of design, because we have the XCDs and the CCDs. They are interconnecting each other by the infinity fabric link. Okay, each one is connected to the infinity fabric. And we have in the MI300A APU, we have 6 XCDs. Now, each CD has an ACE. The ACE is a synchronous compute engine. ACE is a synchronous compute engine. Okay, AECE is a synchronous compute engine. But the ACE in AMD GPU, we have this MI250X GPU. The ACE is something like a job scheduler for these GPUs. It is in charge of scheduling the threads to be in charge of dispatch the workloads onto the GPUs. For MI250X, we have 2 GPUs on a single die. Basically, you have 2 ACEs. Basically, you have 2 ACEs. You have 2 ACE per MI200X discrete GPU. You have 1 ACE per GPU. And ACE is going to take the workload from this queue and dispatch the workload onto this GPU. Okay. But there is if you look at this MI250X, MI250X, if we think this is MI250X, it has only two XCDs, and you have only two ACEs, one ACE per GPU, okay, per XCD. But here, because this architectural evolution, basically right now on MI300A APU, we have 6. This is the last one, as if that's going to be the number 5th. That's the 6th one. It starts from 0, so it's the 6th one. You have 6 XCDs, you have 6 GPUs. And the 6 GPUs, you have 6 ACEs per GPU. And we have this the green line number 3, and this line is it is kind of a kind of a synchronous link between these ACEs. So that means these ACEs, this asynchronous compute engine, they can work cooperatively. Cooperatively means that if you have workload, you can, let's say, you can put the first, you can take a workload, you can put the first one here for XCD 0, and then you put the second onto XCD 1, and etc. etc. Basically, you can make these XCDs to work cooperatively. So MI300A allows the kernel scheduling hardware on each XCD, means the ACEs, to work cooperatively with other XCDs to present to user mode software a multi-XCD partition. Okay. Here is that we can make these 6 XCDs a single partition. We can make these 6 XCDs 3 partition. In case of 3 partition, you are going to have 2 XCDs per partition. In that case, each partition is just like MI250X. You have 2 XCDs on the chip. Okay. But the reason to do that is that here is a high-level description. Is that that's something like a launch a kernel, and the ACEs on each XCD can work together to process the request, so they can work cooperatively. Okay. Now, this cooperative protocol allows the partition to take a single kernel dispatch from a single software visible kernel and spread the workload across XCDs, making the partition appear as a single logical GPU, despite its multi-chip-like nature. This is a natural pairing to MI300 unified memory, where the entire HBM memory space is visible to a single process. Okay, now here it explains that basically we can make all these XCDs to work cooperatively. If we can have this done, the technical reason is that this is a high-level language to describe the kernel launch request, and then you have all these ACEs communicate each other. So in this case, basically, you can present to the user the 6 XCDs as a single logical big GPU. This is what this is saying. Basically, you can make this as a single big GPU. Okay, this is something very interesting, because we have 2 XCDs per MI250X. That means at maximum you can have these 2 XCDs work together. Okay. But for MI300A, you have the possibility to have the 6 LCDs work together and present them to the user as a single logical GPU. And this is good. Why this is good? Because we have discussed in the previous part that the MI300A has a single memory hierarchy. Has a single memory hierarchy. So if you have a single big logical GPU, that match the fact that that you have a single memory hierarchy for each MI300 APU. So that's a perfect match. Okay, so this gives this APU some. I give this kind of feature. I use this word super capacity. Now this. But we cannot use the word super chip, so I call this kind of capacity. Now I just call it super capacity, because if you make it look like a big logical CPU, pretty much that's a very you have a super capacity. You make the 6 GPUs work together. That's going to be a very, very powerful logical GPU. And it match the memory hierarchy, and that's a perfect thing. So I call this the super capacity of MI300A. Okay, now basically the other part, which is saying that because here the design of this MI300A, they don't put just a single ACE for these 6 XCDs. They put 6 ACE. This means that it uses per-chiplet scheduler to reduce inter-chiplet varying requirements and increase work group scheduling throughput. As you have more chiplets, you are going to have more ACEs. This is saying that basically the ACE can be scaled out. This also enables MI300A to present partitions with different number of chiplets. Okay, so this is the super capacity of this MI300A. This one I have seen from this document. Basically, this is some kind of document from AMD. It's more for academia. It has been mentioned by this document, but I haven't found any customer from the internet. I haven't found any user who have done this kind of usage of the MI300 APU. We need to wait and see what's going to happen with this feature. So just want to mention this is the super capacity of MI300A APU that comes together with the architectural evolution of this APU. Okay, so now we are going to move to another topic, which is a little bit related with this discussion, which is called the NUMA node. Because you know that in section 1, I have discussed the NUMA node. We know that each AMD CPU, basically because it has this kind of chiplet design, you have the I/O die in the middle, and then basically the I/O die could be divided into 4 parts, and each part is going to have some memory and some CCDs. And then this one is going to be called the NUMA node. And then for a CPU, basically you can have 4 NUMA nodes. That's for the CPU. And then look at this one. I'm thinking, because here I read from the paper that this MI300A, you have 3 CCDs, you have 6 XCDs, then basically, naively, I think that, okay, this NUMA node, I'm going to have, because I have 3 CCDs, I'm going to pair 1 CCD with 2 XCD, and then you are going to have a NUMA node. That's my naive thought at the very beginning. And because you have 3 CCD, means that this one you are going to have 3 NUMA domains. That's my first thought. And then for this super tip, this is the hopper, the Grace hopper super tip. You have the Grace, this is the CPU, and the hopper is the GPU. You have 4 sockets per node. This is a node. You have 4 sockets per node. Basically, you have 4 super chips. And naively, I think this you're going to have a NUMA node for this one and another NUMA node here, and at the end you are going to have 4 NUMA nodes, and this one is again 4 socket node. So I think at the beginning, I think that you are going to have 3 NUMA domains, NUMA nodes per socket, and you are going to have 12 NUMA nodes. That's my first thought at the very beginning. And this one, you are going to have 4 NUMA nodes. Okay, 4 NUMA nodes. Is that correct or not? Is that correct or not? So this is my thinking at the very beginning. Is my naivety. Okay, basically that was totally wrong because this is not the definition of this NUMA domain and the NUMA nodes. This is wrong. It's wrong. And let's have a look what's the correct definition of the NUMA nodes and the NUMA domain. Is that here the partition? We have discussed this the super capacity of the MI300A. Basically, you have the 6 XCDs 0, 1, 2, 3, 4, 5. You have 6 XCDs. You can put these 6 XCDs in one partition, or you can choose to put these 6 XCDs into 3 partitions. In the first case, my thought comes from here. In the first case, because you have only one partition, I thought that you have only one NUMA node, and for the second case, you have 3 partitions, and I thought at the beginning, okay, that you have 3 NUMA nodes, and that was wrong. And here, that was my thought at the beginning. I thought that okay, you have per chip is a NUMA node, and then you have 4 NUMA nodes. That was totally wrong. Let's have a look. What's the correct one? This is totally wrong. I'm going to touch that one later. We are going to have a look of this 308. Have a look at this 308. The 6 XCDs can be used as a single compute device or as 3 separate partitions, shown in the above figure. In both partitioning modes, the entire HBM address space is uniformly interleaved, implementing a single non-uniform memory access domain per socket. So why I was wrong? Because here the NUMA node, the NUMA domain, or the NUMA node, the definition comes from the memory. It doesn't come from the partition. You have 3 partitions, you have a single partition, it doesn't matter. We need to have a look of the memory. So for the MI300 APU, we have been discussing that they have it has just one memory hierarchy shared by all the XCDs, all the CCDs, everything is sharing the same memory hierarchy. So it doesn't matter you have only one partition or you have three partitions, because whatever the partitions, they are going to share the same memory hierarchy. And it's really at the end, the memory hierarchy, the memory is going to define the NUMA domain because you are sharing the same NUMA domain. So you have always only one NUMA domain. So one NUMA per socket, one NUMA node per socket. NPS means NUMA per socket. So you always has one NUMA per socket because you always has one memory hierarchy per socket per APU. So even you have three partitions, you have only one NUMA node. Okay, that's for the AMD side. For the Grace Hopper, for the Nvidia part, let's have a look what's the correct definition of the NUMA domain. As I have said, the NUMA domain definition comes from the memory, is based on memory and only on the memory. So in that case, this is a superchip, a Grace Hopper superchip. What we have on a superchip, Grace Hopper superchip, we have two parts of memory. LPDDR5, that's the memory for the Grace CPU, and HBM3, which is the memory for the GPU. Because you have two sets memory with different technology, basically you have two memory hierarchy. That means you have two NUMA domains. So my thought was with total naivety. It was totally wrong. And this is the right definition. So here you have four socket node with four superchips. That means here you have one superchip, you have the second superchip, the third superchip, and the fourth superchip. So in connected superchip, in a quad, Grace Hopper appear as a single device with two NUMA nodes per unit, means per superchip you have two NUMA nodes. In the above figure highlights the different NUMA nodes that compose a node in the Alps supercomputer, which is located in CSS in Switzerland. The four Grace CPUs are associated with NUMA nodes 0, 1, 2, and 3. So this is NUMA node 0 with Grace 0, NUMA node 1 with Grace 1, NUMA node 2 with Grace 2, NUMA node 3 with Grace 3. So that's the four CPUs. And then following a sequential numbering, the four Hopper GPUs are associated with NUMA nodes 4, 12, 20, and 28. So the first Grace CPU is connected with NUMA 4. And then the Grace 1 is connected with NUMA 12. And then the third Grace CPU is connected with NUMA 20. And the last one is NUMA 28. So this is the numbering of these NUMA domains, NUMA nodes for CPU and for GPU for Grace Hopper. This is a kind of numbering that made me confusing at the beginning. I don't know why this is the way for Nvidia to choose to number their domains. But I suppose they have their own reasons. But anyway, we are going to continue our discussion. Probably in the next section, we are going to come back to this point, in which section we are going to have a look of this NUMA ID stuff, and we are going to come back to this NUMA domain, a NUMA node definition for Grace Hopper superchip. And then for the MI300 view, this dotted green line means, this dash line means that there's the NUMA domain. This dash line is NUMA domain or NUMA node. So you have only one NUMA node per APU. And you have 4. So I was naive. I was too much naive. I thought we have 12 NUMA nodes, but actually, what we are going to have, we have 4 NUMA nodes, for AMD MI300 quad socket system, and we have 4 Grace NUMA nodes plus 4 GPU NUMA nodes, 4 CPU NUMA nodes, and 4 GPU NUMA nodes. And this is the definition of the NUMA nodes, and we need to make the things correct. And this is the definition. So pretty much we have finished this part. The last point is that we have been talking about this unified memory of API of MI300 APU. We have this MI300A APU. You have this unified memory. It's really unified memory. It's physically and logically unified memory. And then I just want to mention that at the beginning, before we have this superchip and this MI300 APU available from the marketplace, we already have this CUDA programming environment, and in this CUDA programming environment, we already have this unified memory. It's called unified memory, but it's different from the MI300A unified memory. In the CUDA programming environment, the unified memory really means unified virtual memory, and is implemented by the CUDA runtime by software. So it's not based on hardware. It's based on software. In the early stage, when you are still using the GPUs connected to the host by the PCIe link, we already have this kind of unified virtual memory based on the software, based on the CUDA runtime. And at that time, I think in the Nvidia document, it's called unified memory, and in AMD document, it's called managed memory. And the unified memory is a software solution with the hardware support for sure. Unified memory is a single memory address space accessible from any processor in a system. This is the concept. Basically, if you apply this concept with MI300A, that's totally okay, because if you change this with XCD, and CCD, that's totally okay. So MI300A, it has this kind of unified memory, and the original drawing is showing this concept, this kind of unified memory based on the software implementation from the CUDA runtime. This hardware-software technology allows applications to allocate data that can be read or written from code running on either CPU or GPUs. allocating unified memory is as simple as replacing cores to malloc or new with cores to CUDA malloc managed. So actually it's called unified memory, but in the when you are going to do the programming, you are going to call this managed. So it's kind of managed memory when you use this functional call. An allocation function that returns a pointer accessible from any processor, from the CPU and the GPU. Now, pretty much this is the unified virtual memory. So we need to distinguish this concept. When we talk about the MI300A, it's really unified memory. It's hardware and software unified memory, and for CUDA is a software solution. It's a software solution by the CUDA runtime to give you this unified virtual memory. So this is the something we need to take care of when you read the documents from AMD and Nvidia. So we need to do the summary for this section. We had a look of this Grace-Hopper Blackwell superchip. So the conclusion I draw is that GPU is still a PCIe equipment, but it can access the host memory and its cache is coherent with the host. MI300 APU GPU is no more a PCIe equipment, but a real co-processor of the APU system. It shares the same last level cache and a unified memory with the CPU. It has the same status as of a CPU. I mean, the GPU has the same status as the CPU. MI250X is a product in between Grace-Hopper and MI300 APU, but its logical architecture is more approach to the MI300A. And then we did the comparison between these three products by using a table. These products, notably Grace-Hopper and MI300A, shows to the programmer a unified virtual memory, but with underneath very different architectural evolutions. If you still remember, we talked about that. With this architectural evolution, you don't need to care about this memory copy in, copy out from the host to the GPU. You don't need to copy the data to the GPU and afterwards copy the data, the result back to the host. This copy in, copy out is no more a story for the programmers. It's going to make their life much more easier. And at the last, we discussed this supercapacity comes together with MI300 architectural evolution and the Newman-Knowles definition. Okay. This is end of section 5, and this is a very important section, and it's also difficult to understand. We really need to dive into the technical details, the architectures, try to understand what's the architectural difference, but they showed to the customer the same benefit, which is they don't need to do this host to GPU memory copy in, copy out. But these technical evolutions are so much important. And sometimes I even think the technical evolution comes from this MI300A is a kind of revolution. So this changed the landscape of the GPU computing a little bit, not too much, but a little bit. And afterwards, we can understand that MI300A is the product which compete directly head-to-head with the super chip from Nvidia on the marketplace. So things are getting exciting. So I'm going to conclude this section by saying that the golden age of GPU computing starts from now. Okay, so let's conclude. And this is the end of section 5. I have another section to go. Let's continue. See you very soon. Bye-bye.